Mr. Fiacco and fellow calculus students. This is Sharon.
Hi, this is Rebecca.
And we chose to do our topic on curve sketching. Now to illustrate our topic, we chose to do the graph of f of x equals 2 times x squared subtract 9 all over x squared subtract 4.
Okay, so to graph this function, the first step you need to take is find the x and y intercepts. And then to do that, all you have to do is set y equal to 0. And when you do that for this function, you will get negative 3, 0, and 3, 0 for your x intercepts. To find the y-intercepts, you just need to set x equal to 0, and when you do that for this, you'll get 0 and 9 halves. Oh, and on our graph right here, you can see that we plotted them in the very beginning, got these 2 points, and this point right here.
Then you have to find the symmetry in the graph. So in order to do this, you can plug in negative x, and you will get an equivalent equation, and that will be symmetric to the x-axis. You can also do this with the y-axis by plugging in negative y, and you can do it for being symmetric to the origin by plugging in negative x and negative y. In this equation, we found it to be symmetric to the y-axis, as you can see here.
Can I call you back really quick?
Alright, so then we move on to step 4.
Okay, so for step 4, you just have to find the domain. And to find the domain of the function, you just have to set the denominator equal to 0. So for here, we just factored it, and then we got that x is not equal to and negative 2. And then the vertical asymptotes is pretty much the same thing, but it's what, it is. Yeah.
It's the excluded values that do not exist on the graph. So you set it equals the denominator equals 0, just as you did for the domain.
Yeah, so then you get your vertical asymptotes to be 2 and negative 2 right here and right here. Okay. And then step 6 is taking the derivative of the function, which is f prime of x. And for this certain function, you have to use the quotient rule. And the quotient rule is pretty much just the derivative of the top times the bottom minus the derivative of the bottom times top over the bottom squared. And then once you do all of that for the function, you will get f prime of x equals 20x over x squared minus 4 squared. And then
you have to find the critical numbers, and you do this by setting the derivative equal to 0. So once you do that, you will find that the critical number is only x equals 0. Then you have to take the first derivative test. You can do this by plotting them on a number line, or you plot the critical numbers and the vertical asymptotes on it, and then you plug in numbers in between the intervals or regions, and if it's negative, it will be decreasing, or the original function will be decreasing, and if it's positive, then it will be increasing. You can see this over here, that it's decreasing from infinity to negative 2, and it's decreasing from negative 2 to 0, and it's increasing from 0 to 2, and increasing from 2 to infinity.
Then step number 9 is taking the second derivative, and that's pretty much just taking the derivative of your first derivative that you already got earlier. So to take the second derivative of this, you have to do the same thing you did earlier, which is just the quotient rule again. So once you apply that to this, you will get this for your second derivative.
Now moving along to the next one. Ronnie, get down. Alright, so you have to take the pips, which are possible inflection points.
Okay, and to get the pips, you just have to set the numerator equal to 0. But in this certain function, you have no pips because you can't take the square root of a negative. Like right there.
Okay, in step 11, you have to take the concavity test. You will use the pips that we found earlier and the vertical asymptotes. For this problem, we have no pips, so you only have vertical asymptotes. You will plot the vertical asymptotes on a number line and find if it's increasing, or if it's positive or negative by plugging back into the second derivative. By plugging these in, you will find that the original function behaves
like concave down, concave up, and concave down.
As you can see here, concave down, concave up, and concave down.
Okay. Step number 12 is finding the inflection points, which pretty much you just have to check for if the pips are in the domain. But remember, back here we have no pips, so therefore we have no inflection points.
Now for the horizontal asymptote, you will look at the degree of the numerator and the denominator. If the numerator is greater than the degree of the denominator, then the horizontal asymptote doesn't exist. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote equals 0. In the case of our problem, the degree of the numerator is equal to the degree of the denominator, so the horizontal asymptote equals the ratio of the leading coefficients, which is 2 to 1. So our horizontal asymptote is y equals 2, as you can see here.
After putting all 13 steps together, we were able to graph the whole entire function right here.
And yeah, and we got our cool dinosaur here. And
Our elephant, where is it? Oh, it's over
oh, and our elephant is right there.
Oh, you're so cute.
Oh, there he is. This is Ronnie. He barks a lot.
Oh, wait, oops. There.
Oh. And we have our amazing film director,
Nathan!
Nathan Buckwood, who stepped up to the plate because no one was home. Woo!
Okay, and that's all.
All right, bye.